a bunch of colleagues of whom I wasn't one published an article that was the first article to really, or first study to attempt to do full microphysical studies of particle formation in the stratosphere. The previous modeling experiments have either just prescribed a change in solar forcing, or they put in sulfur, but they haven't allowed the sulfur to determine what size the particles were. That's not quite true, but it's almost true. And what this result found, which used a sort of state-of-the-art 2D model that's been tuned up on the Pinatubo experiments, is if you put sulfur in continuously, you get, at least in this version of the model, but we think the underlying physics is pretty robust, although the numbers aren't, you actually get a remarkably ineffective result. So you had to put a great deal of sulfur in to get enough radiative forcing. If you look on that right-hand one, even if you put 10 megatons a year of sulfur in, which is a huge number, by this model, you only get about a watt, 0.7 of radiative forcing, which is much, much smaller than previous predictions. And that's because you've grown particles that are too large that are falling out very quickly. And there may be some ways around that, but that underlying fact that if you put in a gas, the gas all ends up in the existing particles, the particles get too big and fall out, is pretty likely a robust result. So more or less, you could say, this says that the standard way people have thought about doing this doesn't work, or at least doesn't work very well. The novel method we've been thinking about, or it's not novel at all, it's actually exactly what happens from aircraft contrails. The novel method is that we put a condensable vapor directly out of the back of an aircraft. And that's what happens with water vapor out of the back of an aircraft. The water vapor cools by mixing with the ambient air, and then it condenses to form particles. That's the mechanism of contrail formation. So if you did that with H2SO4 directly, putting it in as H2SO4 instead of as SO2, you find that the formation of particles is completely dominated by dynamics that happen in the plume in a day, and essentially has nothing to do with the background particles. And we've tried this with the state-of-the-art. I mean, it's both true when you do back-of-the-envelope calculations, but also we've tried it with a state-of-the-art nucleation code, and it appears to be true in that code. This gives you a quick look. Actually, maybe I'll skip in a second. This gives you a quick look at results. If you look at the upper panel and you look at the black line, that's the particle number density. That's what happens with SO2, where you get a bunch of these very fine particles, but overall you get particles that are quite a lot larger. There's the black line on that log scale goes quite a bit more to the right. Whereas when we put particles in directly, effectively by taking the output of the plume model and feeding it into the 2D model that does particle size dynamics, we get results that are much more effective. I'll skip this. And that's one of the preliminary answers. We're actually looking at two different radiation codes, so this is not exactly the same as what I showed you before, but the ratios are the same. When we put in particles directly, we get a much more effective system. So we can find that a few megatons a year of sulfur would be enough to produce sort of 4 watts per square meter radiative forcing. Not that there's any reason you should want to do 4. I think some of the conversation about geoengineering has been caught by a kind of foolish dichotomy between doing nothing or doing enough to compensate for 2 times CO2. I think it's almost certain that would not be sensible policy. But nevertheless, at the level of simple modeling, this gets you a sense of how much more effective it is if you can control the particle sizes better. So thinking a little more generally, you can think that there's actually quite a few means of putting particles in the upper atmosphere, and essentially all the effort so far is focused on number one. You put in this high vapor pressure gas, it converts to a low vapor pressure gas, and I think that it inherently makes it extremely hard to control particle sizes, and I think that will be a general fact of any analog to that. We've talked about method 2, which is a low vapor pressure gas. The advantage of that is it turns out there's a huge literature in the nanofabrication world about making fine particles. I'll show you a picture in a moment from low vapor pressure gases. People understand how to do it pretty well, and there's nothing very hard in terms of aircraft engineering. If you go to aircraft engineers, and we've done this, they say, that would be easy, we could do this if you want us to. Whereas number 3 or number 4, putting in solid particles or making fine droplets, is much harder because it relies on spray technologies that may not exist yet. We've mostly thought about sulfur, and there's a lot of good reasons to think about sulfur because sulfur's what nature does, and there are very good reasons to think we would like to start very slowly if we ever wanted to do this and do something that was an analog to nature because we have some idea what the downsides of what nature does are. Nevertheless, there might be some good reasons to think about alumina. It turns out, first of all, there's been a lot of work on the environmental consequences of alumina in the stratosphere because it's in shuttle exhausts. There's a bunch of papers going back to the 70s that look at the radiative and ozone-destroying properties of alumina in the stratosphere, and those make you think it might be useful. The big deal really is that alumina has 4 times the volumetric radiative forcing for small particles as does sulfur. And that means you have 4 times less surface area for the same radiative forcing. And this is a much bigger deal. You'd have roughly 16 times less the coagulation rate. And that's the thing that really drives removal. So you could get away, we think, with much smaller mass fluxes. But we haven't run those studies yet, so that might be wrong. The little picture is from a nanofabrication study, which shows you can make very high quality, and do this in just a jet in a very simple way, make high quality alumina particles just by spraying alumina vapor out, which oxidizes. So it's certainly in principle possible to do that. There's a big literature that's already looked at that. We've been doing a little work on delivery. There's a study that an aircraft engineering firm called Aurora Flight Sciences is doing, and all the results of that study will be completely public. There's nothing proprietary about this. We're going to be inviting people in for a mid-study meeting soon. And they've been looking at a bunch of different delivery options, but the bottom line is that it seems pretty cost-effective and easy to do this with aircraft that are not very different from conventional aircraft. So there's no, from their point of view, nothing radical and hard. For them, radical and hard is making aircraft that fly at 100,000 feet, but not ones that fly at 70. Give you a little sense of some of that. One thing that study's turned up is that some high-class business jets, like the Gulfstream, have wing designs that are very efficient. So with slightly different engine choices, they can easily deliver large weights up to sort of 20 kilometers or a little higher. And you could do that by either building new versions of these aircraft or even re-engineering existing aircraft. So there's some ideas of that. There are now studies you see on the lower right. These are preliminary. Look at the total cost to deliver a megaton a year to the stratosphere as a function of height and so on. The bottom line of this is simply sort of confirming earlier work that Alan's done, that it's so cheap that it doesn't matter. So the fact that it's cheap isn't necessarily a good thing at all. As I'll come to in a second, the fact that it's cheap is part of the hard problem of governance. The fact that it's cheap means any small state or even conceivably individuals could do this, and that is a very dangerous thing. So the fact it's cheap is not necessarily good, but I think it more or less is a fact. So this is where I would push back on the statements that it doesn't exist. I mean, it doesn't exist in the sense that you can't just do it today, but exists in the same sense that if you wanted to build a kilometer-high building or lots of big ships today, we have engineering firms that can do it. So you go to an engineering firm and you want this done. They don't say this is hard or unusual. They say, okay, yes, we could do it. So a few closing thoughts on this. What I said at the beginning, it's much easier to think of new methods that might conceivably offer lower environmental risk for the same radiative forcing than the existing methods. That's the point of this from my point of view. There's a huge scope for new methods, because once you realize you can make things by direct condensation from vapor, then all sorts of different compounds are possible. But it's much, much harder to actually figure out the environmental risks and effectiveness of these new methods than it is to cook them up. And that is going to be a fundamental ongoing problem here. So now coming back to the things I said at the beginning, I said that solar radiation management was cheap, fast, and imperfect. Now let's think about the policy consequences of being cheap, fast, and imperfect. So, sorry, I've repeated the slide. The policy consequence of it being cheap is control. So if you think about the problem that we have for controlling CO2 emissions in the atmosphere, the problem is to, if we want to cut emissions, get many different states around the world, many different individuals to collaborate on a very costly activity, which, I mean, I spend a lot of my life trying to convince people to collaborate on, and whose benefits are spread globally. And that's inherently a hard thing to do. It's the commons problem. Aerosol geoengineering looks like it is so cheap that the cost is basically not going to be an issue. That means that implementation decisions will be risk-to-risk decisions. The risk of doing it against the risk of not doing it. And it makes the problem of how we govern it fundamentally harder and different and novel. It's fast, I said that already, and it's imperfect. It's just basic physics. Both all the models say so, but don't believe it just because the models say so. Really, basic physics says that reducing the amount of sunlight is just not the same as reducing the amount of CO2 for a bunch of reasons. So we should expect that for fundamental reasons, you cannot compensate for the amount of CO2 in the air by doing this completely. You may or may not, in a useful way, reduce the risks, but you can't compensate it away. And the policy consequence of that is, it is not a reason